Welcome to example number 16. In the track shown below, section AB is a quadrant of a circle of radius r. The block is released at position A from rest and slides down without friction until it reaches point B. At point B and then on towards a distance d, it encounters friction that will eventually cause it to come to some halt, and we'll just call this point C over here. So we're asked a couple things. We're asked to find out how fast is the object moving at point B. And we're supposed to derive our answers in terms of G, R, and D. So let's go ahead and solve this. So in part A, we're going to use conservation of energy. The energy initially at A must be equal to the energy finally at point B. So when you start off at A, you could say, well, you have kinetic energy, but that velocity A is actually 0, so there's no kinetic energy. So really all you have is the potential energy, mgha, and then at the bottom we're going to have kinetic energy, 1/2 mvb squared, but do we have any potential energy at that spot? No, we're going to assume that this potential energy here is 0 because we're going to assume that height b, this spot right here, this location has a height of 0. So essentially, the potential energy that the block had at A is converted solely into kinetic energy at the end. You'll see the masses cancel out, and hopefully you'll realize that the height at A is really the radius of this quadrant of the circle. So height A is R. So we're going to replace H with R, and then we're going to be solving for the velocity at B. So the velocity at B should be equal to the root of 2gr. Okay, moving on to part B. We're asked to determine if when it moves from B to C, it slides the distance d and comes to a rest. What would be the coefficient of kinetic friction as the block slides? So there's a couple approaches that you can follow. One could use dynamics and draw a free body diagram for it, but let's practice, since this is an energy chapter, let's use our idea that we developed with work done by friction. So the work done by this force, this external force, is causing that change or loss of energy. So the energy finally minus the energy initially is equal to the work done by friction. Now the work done by friction is calculated by taking the force of friction multiplied by the distance and then multiplied by the angle between the force vector and the displacement. So we can continue a little bit on the right side. Actually, let's replace the force of friction with mu Fn. Let's replace the distance delta r that it slides as d, shown in the diagram, and the angle between the force of friction, which is in the opposite direction that it's moving from B to C, but the force of friction is acting in the negative x direction. That would be a cosine of 180 degrees. And then final energy. Now, the energy it has at C is really nothing. It doesn't have any energy because it lost it all. And the energy at B, we could use either A or B. It really doesn't matter. Let's go ahead and use the energy, I guess, at B here. So it'll be 1/2 m velocity of B squared. So this right side is negative 1/2 mvb squared. And the left side is now going to be, let's replace Fn with m times g, because the normal force will be balanced out by the force of gravity. Remember that friction will be repelling backwards here. And then we have cos of 180, which is negative 1. So you'll see that these two negatives will cancel out. Okay, we're almost there. The mass will cancel out. And we can also replace velocity b squared with the root of 2gr quantity squared. So we have mu gd equals the right side. And that right side, if you square it, you're going to get 2gr, and the 2's cancel out. So mu gd is equal to g times r, and g's cancel out. So in the end, you basically get mu equals the ratio of the height that A was released at, which is the radius of this quadrant, divided by the distance that it slid. And that's it for this example.